Okay, good afternoon. We're talking about the EM algorithm. The first thing you should know about the EM algorithm is that it's not an algorithm. It's more appropriate to call it a method. The reason it's not an algorithm is that algorithms, by definition, are fully specified, consisting of atomic operations that are well defined. The EM method is a method for solving the maximum likelihood problem that does not, the specific steps are not fully specified. Sometimes you can fully specify them, sometimes you cannot, or you don't know how to. So that's one important side comment. When does the EM, I'll still call it EM algorithm because everybody else does, but you should know it's not an algorithm. When does the EM algorithm come up? When we're looking for a maximum likelihood estimate and we cannot solve it analytically. Okay? So the whole purpose of the EM algorithm is finding a maximum likelihood estimate of some parameters when the likelihood function cannot be maximized analytically. When does that happen? Find the maximum likelihood estimate from data when analytical solution is not possible. So there are several scenarios that lead to when it's not possible. One is when latent variables are involved, latent and unobserved. Are involved. Which is not to say that whenever there are latent variables, you cannot solve it analytically, but often that's the case. I should, instead of saying are involved, are part of the generation story. Let me rephrase that. On the generative story, generative story involves unobserved steps. Unobserved steps can be represented by variables that take on values based on these unobserved steps, and these variables are not observable, they're latent. A second and related case is when the generative story, maybe there is no generative story, but the structure of the likelihood function is such that you could think about it as if it were a generative story with latent variables. What do I mean by that? Remember that with the source channel paradigm, we had examples of coming up with generative stories of the source channel paradigm that didn't make much sense. Like that when you want to translate from English to French, the sentence used to be French and got converted, right? But the form of the solution, the Bayesian classifier, could be interpreted that way. And it's the same thing here. So the example I gave for the first one was of the two Gaussians. Choose which Gaussian. choose A or B. and then draw x from A or draw it from B. Remember that? We had two Gaussians. This is clearly a case of one, when the generative story that you're told is there was a flip of a coin somewhere here, the output of which we don't know. We will never know. Nobody ever tells us what the output of the flip of the coin is. But based on that flip, we drew either from here or from here. But now I'll tell you a different story that has nothing to do with generative story. I'll just give you a model that would have a similar behavior. So let me write the model for this. The model for this is the likelihood of the data, of a particular data item, is sum of, this is lambda A, and this is lambda B. These are the probability of the coin falling on A, probability of the coin falling on B. Lambda J times probability according to, of X according to mu J and sigma J. This is the mixture of Gaussian story, right? It doesn't even have to be 2. So let's make it 1 and 2, and this is J, and this is up to L. This is the mixture of Gaussians. Now it's no longer a coin. It's some kind of a random process that assigns a multinomial with L possible outcomes. And I push the button, I get back one of these. And whichever one I get, I go there and use that Gaussian to generate X. Okay? So this is the complete likelihood of X. It sums over all the possible choices of the right Gaussian, each with its own probability, lambda J. So I can write here, there's a, what do I call it? H comes from a multinomial with parameters lambda, right? Lambda 1, lambda 2, lambda L. Okay, everybody with me? This is just a mixture of Gaussians, and this is the likelihood function. Now, go back to our discussion of n-grams. We had unigams, bigams, trigams, fourgams, and so forth. And we said that they each have their own bias-variance trade-off. The higher the order of the n-gram, the lower the bias, the higher the variance. And we had this idea of shrinkage. We're going to combine them together using linear interpolation. And we even discussed the question of how to choose the weights for the linear interpolation. What was the form of the final model, the linear interpolation model? P of a word given the history, according to the linear interpolation model, was a weighted sum, lambda J, of the probability of the word given the history based on the jth component. Unigam, bigam, trigam, fourgam, right? J goes from 1 to L. So it's exactly the same likelihood function. And if it's the same likelihood function, we can use EM in the same way. Now, to force this into the interpretation of that we had there of the generative story would be to say that the way the next word in the history is generated is we first choose randomly, based on the parameters lambda, which model to generate it from. And then we take that model, be it a unigam, bigam, trigam, and we generate that word from it. But we don't really believe that that's how words are generated. Right? So it's not really a credible generative story. But mathematically, that's what this formula says. It says, if you want to generate according to this model, every word, every time you're about to generate a new word, first choose which model to generate, which component model to generate from. If you chose unigam, now generate from unigam. If you chose bigam, now generate from a bigam. So they are indistinguishable. It's the same likelihood function. It's just that one of them came from a truly generative story that involved the latent variable, and the other one just has the likelihood function that looks like it. So this is what goes here. So I'm saying when the generative story involves observed states, I would say when the likelihood function has the form that looks like 1. Has the form that looks like the generative story involved unobserved steps. The third case is simply when some of the data is missing. Some of the data is missing, and therefore some of the data is missing, and therefore the likelihood function would look like the generative story involved unobserved variables. So what would be an example of that? Suppose I'm back into the mixture of Gaussians, but the person who recorded data did record which Gaussian was used for each data point. They flipped a coin, or they used a multinomial to choose which Gaussian component to use, and then they wrote down the x, and then they did it again and again. If they always wrote down which was used, I don't need EM. We showed that we can separate the data based on, for each Gaussian, give it the data points that it was used to generate, and then use simple sample mean and sample variance to estimate the mean and the variance of those Gaussians. But let's say that some of the data was lost. Maybe some of the recordings of which Gaussian was used was lost. It doesn't even have to be that it was lost for all the data points. It may have been lost for just some of the data points. The original EM paper, which is in 77, I think, the title for it is a method for maximizing likelihood with incomplete data. And the example they gave was from data that's just missing. Missing because it was lost, missing because it wasn't recorded, missing because we just don't know why it's missing. It's missing. In practice, when we today use EM, we usually use it for one of these cases. Either we really do believe the generative story involves some latent events, but we don't have access to them. Sometimes we even have access to them, but it's expensive to get them, so we give up on getting them. Or it's like this case, where the likelihood function just has a shape that cannot be directly maximized analytically because it looks like it had some latent events. All right, now let's look at the EM method itself. There's always a problem with what to use X for and what to use Y for. Unfortunately, Z is always used for the same thing, and X and Y are used inconsistently. So let me decide which one I'm going to use today. I don't know. You will find papers with both. The original EM paper actually uses the method I don't like, or the notation that I don't like. So let's stick with X being the observed variables. Just remember that if you look at papers, keep in mind that people might have flipped the two. So just ask yourself, which is the observed and which is the unobserved? Observed variables. And the unobserved I would call one of two things. I would call either H for hidden or Z. Z is what's usually used in statistical literature. I'll call it H here. It's easier to remember H hidden. The combination of both observed and unobserved is called the complete theta. And now we're given the observed data, which is x1 through xn. Our goal is to find the MLE of some parameters. Namely, so the bar is to show that it could be more than one parameter. Typically, there are many more. The hat is to show it's an estimate. MLE would be the one that maximizes the complete data likelihood. So that means the P of, call it Y, conditioned on data. This you're familiar with already. I will write this as argmax over all theta. First, I will convert it to log probability. The thing that maximizes the full probability also maximizes the log probability. It's the usual thing. So it's log probability, and instead of y, I'll write it explicitly as x and h given theta. By the way, I put the bar over the theta, but there should be bars over the x and the h too, because there could be many x's, many h's. I'm sorry, it's not the same kind of bar. This is bar over parameter values. This is, well, yeah, they're vectors. They're x1 through xn. So they're also bars. Now we have a problem. The problem is that we know x, but we don't know h. Right? H is, by definition, hidden. So what do we mean by maximizing the log probability of the joint distribution? Since we don't know h, and in principle we will never know h, we can't know h, we have to take into account all the possible values of h, all the possible values that h can be. And we want to, some h values are more likely than others. So we don't want to just sum over all possible values of h, each with equal weight. So what we really want to do is to say, given this x, how likely are different values of h? Literally come up with a distribution over the possible values of h. If we do that, we can convert this into an argmax over log probability, over the expected log probability of x and h given theta. Expectation with regard to h. Namely, expectation is in the form of integration or summation. You integrate over all possible values of h. If it's a discrete set of values, it's a sum. But in the expectation is not just a straight sum. It's a sum weighted by how likely each one is. Okay? So how is h distributed? Namely, what weight should we give to every possible value of h? What does the value of h depend on? I'm sorry? It depends on x for sure. Right? For some values of x, for example, in the case of our two Gaussians, if I got a x data point that's way, way positive, it's much more likely that the coin said use the Gaussian on that side than the Gaussian on that side, right? So it depends on x. What else does it depend on? It depends on the parameters, right? Because where the Gaussians are is the parameters. So it depends on both of these. So now we have a problem. We have a recursive problem. We've converted our problem into one of, instead of maximizing log likelihood, maximizing the expected log likelihood. That's okay. But the expectation is with regard to some weighing of the unknown variables, the latent variables. And the weighing, we want it to be based on what x is and what theta is. We know what x is, but we don't know what theta is. Here we're assuming theta. This is a conditioning thing. So we have a chicken and egg problem. If we knew the real values of theta, we could calculate the proper weight for every h, and then we can take the expectation of this and find the value of theta that maximizes that. But if we know the value of theta, we don't need to do that, right? So whenever you have a chicken and egg problem, just wait a long enough generations. Have chicken and egg and chicken and egg and chicken and egg, and at the end you wouldn't care. That's what we're going to do here. We're going to do a iterative process of assuming some chicken, and then from that deriving the eggs, and from that deriving the chicken and deriving the egg. And we're not going to prove it here, but we're going to state that there is a proof, there is a theorem that says that this will converge. So the chicken we're going to assume is some tentative values of theta. So we're going to initialize some values of theta. Call it theta 0. And then we're going to calculate the expectation over all possible values of h, conditioned on the data, which is fixed throughout the process, and the tentative values that we have for theta, which I will write here as k. Expectation of the log probability of x and h given theta. Now, I want to emphasize the difference between this theta and this theta. This theta is a fixed number that was fixed in the previous iteration, or a fixed set of numbers that was fixed in the previous iteration. This theta is a dummy variable. Dummy variable means a variable that sits inside here, but as soon as you leave this maximization operation, it doesn't exist anymore. It's just it's like for I goes from 1 to 1,000, do something. The I doesn't exist outside that loop.
I have a question.
Yeah.
In the example that we saw last time, we had some conditions on the initialization of theta. In the general algorithm, is there something which states what the initialization should be for?
No, there isn't, because I will get to what the algorithm guarantees. And when I get to what it guarantees, you will see that the conditions, strictly speaking, don't need to be there even in the first case. It guarantees converges to a local minimum. And if you start, well, actually, it's not true. If you start with all the means being the same, it is an unstable equilibrium. And you will stay there, but it's not a local minimum. I think it's a local maximum. Right, but he's asking is how can you generalize the statement that you have to avoid in the case of the mixture of Gaussians, can you generalize it to the general EM statement? So just to keep you all in the loop on what we're discussing, when we talked about the mixture of Gaussians last time, we said, let's suppose even there are only 2 Gaussians, start with any 2 numbers, but they have to be different. They can't be the same number. What happens if you start with the same number? Well, if you start with both mu's being 3, the Gaussians are completely overlapping, they're both in the same position, they're never going, well, actually they are going to move. The first step, they're going to move to the mean of the entire sample, and then they're going to stay there. Okay? That's not a good answer. It's not a good solution. It is not a high likelihood solution, but it's a solution you can't move out of because it's actually a local maximum. Any slight deviation between the 2 Gaussian will result in a better likelihood. I'm sorry, it's a local minimum. I forgot. We're trying to maximize the likelihood. So usually the EM function will converge to a local maximum. This example, this degenerate example, is a
saddle point.
It's a saddle point.
Yeah, it's a local maximum along the line of the 2 means being equal, but on the other direction, it's a local minimum.
Is that right? Well, what's the other direction?
The direction where the 2 means can be different.
If the means are different by a small infinitesimal amount, the likelihood will be better, will be higher. Any deviation from that point will be better, I think.
Yeah, it's just that if you start with equal means, that direction will never be explored.
Right. So I think it's a local maximum, but it's
It's local maximum in that restricted
right.
space.
Right. Anyway, it's a special case, and your question is well taken. How do we put into our general EM formula exclusion of that special case? I know how to do it in practice. In practice, whenever you start with some values of theta, make them all different from one another. But can I give you the theoretical requirement, exactly what you need to avoid? I don't know. But these are sort of archaic or bizarre cases. The general case, you don't have to worry about it. Anyway, I'm taking the max here, and I'm assigning it to my next.
Quick question.
Yes.
I know the theta and the argmax is a dummy.
Uh-huh.
Should it be a dummy theta bar or is it just a dummy theta?
No, it's not really theta bar. If I forget to put the bar, it should always be there. All of them should have a bar. And now I will use that to define my theta bar k plus 1. So I have only 2 steps, initialization and then a 1-step update. So where's the EM here? Well, I expressed in one expression 2 steps. Well, if you want to know where the EM is, this is the E, and this is the M. So EM stands for expectation maximization. Sometimes there's an alternative formulation where people convert this into 2 steps. The E step, you just calculate the expectation of the log of P x of h given theta k. You don't maximize over it, but it's still expectation over h the condition on x and theta k. I'm sorry, this is not theta k. You should correct me. This is the random variable, the dummy variable, but it's not going to be dummy now. And this gives you a function that depends on your theta. It's not going to be a dummy thing. So it's a function of theta. So the E step derives a function which we'll call Q, which depends on theta. It also depends on the x. It doesn't depend on h because we integrated over it. It depends on x, but that's implied. But we're going to show explicitly it depends on theta k. Okay? I'm doing exactly the same thing I did here. I'm just writing it a little differently because you will find that form. So this is a function of this variable, the dummy variable that we had before, except it's not dummy now because we didn't find the max. We just calculated a function that depends on it. And it's conditional on whatever we plugged in as the previous iteration. So this is the E step. And the M step is to say that theta of the next iteration is defined as the argmax over all theta of this Q function, theta, condition on theta k. So I just took these two steps and plugged them into one. This function is called the auxiliary function. What has been proven about this procedure? What's been proven is that for any k, the likelihood of the data so it's not the likelihood, it's the expected likelihood, expected log likelihood of P of x and h given theta k plus 1 when compared to the same thing for the previous iteration, expected log likelihood of P of x and h given theta k. So I wrote the same thing twice, but this is for k plus 1. This is for k. This is greater or equal. So the thing that I'm in search of, which is to maximize this expression, actually it's from here, as I go from iteration to iteration, that thing will grow. Grow and grow and grow. By how much, I don't know, but it will grow. That's the only thing that the algorithm guarantees. Strictly speaking, it's grow or equal. But suppose I can prove that this expression that I'm after is bounded, cannot grow above a certain amount. So if it's bounded, if the complete likelihood is bounded, and to prove that it's bounded, it's enough to show that this is bounded for any h. Because this is expected value. So if it's bounded for any h, the expected value is bounded as well. If it's bounded, then the series will converge. To a local maximum. That distinction of whether likelihood and bounded is important, because if you remember the example we had on Monday of two Gaussians, but we're not predetermining the variance. The variance are allowed to go small. If we apply this procedure to estimate the parameters including the variance, the procedure will never terminate because it will keep pushing the variance. Remember, the solution was that one of the Gaussians sits on one of the data points and pushes its variance lower and lower and lower, smaller and smaller, and then therefore the Gaussian goes up to the sky, and it's not bounded. So the likelihood will keep growing higher and higher and higher. If you can avoid that, if you can put some bound, no matter how high, then the EM algorithm will converge to a local maximum. Is local maximum good enough? Sometimes it is, sometimes it isn't. Certainly there are cases where the likelihood function is convex, in which case local maximum is also the global maximum. That's the case we saw with linear interpolation. And the only thing we were trying to optimize is the weights of the linear interpolation, right? You wrote the code for that, and you saw how quickly it converges. That was effectively doing EM, but in a likelihood space that was convex. The more interesting and the more common case is the likelihood space is not convex. And then sometimes you find answers that are close to optimal or that are good enough, and sometimes you don't. It really depends on the problem. If you take HMMs, which we'll talk about next, it's a classic example of the EM applied. Again, it depends on where they're applied, but when they're applied in speech, for example, it's not usually good enough. It's a notoriously difficult problem to run speech, to train speech models using AM and to get decent models. If you start from something random, there's a good chance you'll get lousy models. Other times, in practice, it works. I don't know much of theoretical results about when it works and when it doesn't, except I know that in practice there are problems where running EM is good enough, and there are problems where running EM is not good enough. It doesn't give you good results. One thing you can do to try to fight it is to run EM multiple times, starting at different starting conditions. That can help you sometimes get better results. It doesn't solve the full theoretical problem because the space is usually high dimensional. It can have many, many local minima, local maxima.
What are the advantages of using the EM algorithm over some other optimization technique like gradient?
Very, very good question. EM versus gradient descent. First of all, they're different. They will end up in different places. I mean, they could end up in different places. One way to see it is gradient descent. Now let's look at gradient descent in one dimension. If you started here, this is one dimension, x, and this is the likelihood. If you started here, gradient descent will calculate the gradient and will take you down here, and if you take small enough steps, you'll end up here, which is not the lowest point. EM, the best, I mean, there's a lot of work on visualizing and explaining EM. The best one that I can relate to you is that EM will do something like it creates a convex function that touches on this function in a couple places and is a lower bound for it or an upper bound for it, and then it finds analytically the minimum of that convex function, and then finds another convex function. That's the auxiliary function. The auxiliary function here can be thought of, it's also a function of x, if you remember implicitly, can be thought of as an approximation, a different function, not the true likelihood function, but a different function that bounds the likelihood function and that is easy to optimize analytically. And therefore, we can find the max of it analytically. So one way to summarize this is to say that EM can jump out of tight places. Another important practical difference is that gradient descent requires typically many more iterations than EM. EM usually converges in small, as in 5 to 10 iterations.
Also, you don't have to worry about setting the step size.
You don't have to worry about choosing a step size. Gradient descent can take thousands of iterations to converge.
Sometimes you do diverge if your step size is too large.
That too. I think you can. There are definitely cases where you can apply both gradient descent and EM. Trying to come up with a general answer. What would be a good example? Well, you can always apply a discrete version of gradient descent called, what is it called in AI? When you do a search in your area. I'm missing the word. Even if you cannot calculate a gradient, you can take the point you're at now and calculate the likelihood there, and then take another point around it, points around it, calculate the likelihoods there, and step in the direction that's the lowest. That's sort of a discrete version of gradient descent. But if you can calculate, let's put it this way, if you can calculate the expected likelihood, then you should be able in principle to calculate the derivative of that with regard to your parameters. The difficulty that you brought up is how do you calculate the expected likelihood when you have hidden variables? And the answer is, if you're assuming that you know the parameters, you know the distribution of the hidden variables. So you have to do some kind of summation or integration over all of their values.
So about that graph, I don't understand how maximization fits this curve and finds an intersection between the convex curve and the real curve. So I guess what I'm trying to say is that the auxiliary function is convex, therefore it forms a convex curve, and then finds the intersection, or like I just don't.
Yes. So I mentioned originally that EM is not a guaranteed algorithm because you may not be able to solve it. And there are two places where you can fail. One is in the E step and one is in the M step. So you can write this function, write it explicitly, and then say, okay, how do I find its expected value? And you can stare it and not know how to do it. There may not be an analytical solution. That's the less common case, but it does happen. The second and more common case is that you were able to write it down and write it analytically as an auxiliary function and wrote it here, and now you come to maximize it, and you don't know how to find the maximum. You don't have an analytical solution to the maximum. That can happen too.
But how is this related to the curve?
I'll get there. So in the cases where you know how to solve it, you can think of the Q function as an analytically minimizable function that has some properties. For example, when this theta is equal to this, it's usually expressed not as this likelihood. Q function expressed as this likelihood minus the likelihood based on theta k. So it tends to have a 0 when these two are the same. So you can then think of this bounding function as, this is Q, it is, this is not x, this is the parameters, right? Theta. As a function of theta for some iteration, but the important thing is it depends on theta here, and which can be minimized. And then you minimize it, however way you minimize it there. I mean, if you have a way of minimizing it geometrically, you think about it, I've minimized it. And that is guaranteed to bring me closer to this. By the way, I may be doing it the wrong way. We're not looking for a minimum, we're looking for a maximum.
So if you're looking for a minimum, it should be an upper bound.
Right. I'm looking for a maximum. And is it in the maximum setting, is it an upper bound or a lower bound? It's a lower bound. So it's a bounding box that goes maybe like this. I don't know, it doesn't have to be exactly here, and it doesn't have to look like this. It can touch it many places. But the idea is that this function touches it at the point theta equals theta k at the previous iteration. That's why we said that theta, when they're equal, is 0. So well, I'm sorry, it's not 0. This minus this is 0. I'm sorry, I'm waving my hands too much, but let me try to maintain the intuition. I know something about it, that it touches at one point, and I know that I can find its maximum. So I go and find its maximum. And then I start from this point, and now I come up with another auxiliary function that it also touches at this point, and it didn't have to be in the same place, so it might be here. Maybe its maximum is here. So now I start from here and create a new lower bound that is convex and that is easy to maximize, and I follow that one and so forth. By the way, there's one more iterative procedure that has somewhat of a flavor of that, and that's the Newton-Raphson method. Are you familiar with that? Newton-Raphson method is a method for finding the zeros of a function. It's not exactly the same, but it has a similar flavor in the sense that you start somewhere arbitrary and you jump a fairly large amount. You're not doing gradient descent. You jump a large amount based on the curvature or on the slope of that place. And it has a similar interpretation that it has a bounding box. Okay, I want to show you how we go from this general case back to the mixture of Gaussian case, little by little, by talking about the special but very common case where the likelihood function is a member of the exponential family. There is a very clear and detailed description of it in the page that is hanging off of our web page. It's only 1 or 2 pages, so I highly recommend that you look at it and try to crack it. Actually, it's only 1 page. The name of the author is not on it, but it's Guy Lebanon, who was an LTI PhD student and went on to become a statistician. So I won't copy everything that's here. I'll just give you the intuition and then you can go over the details. When the likelihood function of x and h is a member of the exponential family, which is not the same as the exponential distribution. There's something called the exponential distribution. There's an exponential family of distributions. Let me try to give you a definition of what it means. It means that the probability of x and h given theta can be written down as some component that depends only on x given theta. Can be written as something that depends only on x and theta times e to the power of a linear summation of hi times some function gi of x and theta. So I'll make that I2. So the data is x1 through xn, and there's maybe parallel with it, there's the h part, h1 through hn. And if you can factor the likelihood of the data as a small writing, as a something that does not depend on the hidden part, and then something that depends on the hidden part through e to the power of. So the log of this likelihood is something plus a linear sum that break down. I don't know, I don't have the right intuition for this except to say that the log likelihood becomes linear in the h's. And since we're going to take the expectation of the log likelihood, this would allow us to move the h's to outside the expectation operator. And all the examples we're going to look at have this form, can be brought to this form. So he shows you here how, what example does he give? mixture of Gaussians, the most classic examples, can be brought to this format. So he will identify for you what C is and what G is. So this is the definition of member of exponential family. Then EM boils down to initialize the theta 0, and then calculate the expectation of each of the HIs conditioned on theta of iteration k. Sorry. So you don't need to bother with the entire likelihood function. You don't need to bother with calculating this whole thing. You can go straight for the kill, straight for these HIs. Calculate their expectations, and then treat those expectations as if they were the actual data. So this corresponds, in the example we did on Monday, to collecting fractions of each point. Which fraction went to the first Gaussian, which fraction went to the second Gaussian. The HI is the variable that is 1 if it went to Gaussian A and 0 if it went to Gaussian B. And the expectation of HI is the fraction of the point that we assign to Gaussian A. So then the third step would be to insert E of HI given K into the likelihood function and maximize. Remember, if this is the likelihood function, then the log P looks like log of C plus sum of HI log of the G. Right? Just took the log of this. And then all you have to do is plug in, instead of the HI, plug in their expectations. Because the expectation with regard to H of log of C of x and theta plus sum of HI log of G of x and theta. Since the expectation is with regard to H, the only thing that matters here are the H's. And because this entire expression is linear in the H's, you can find the expectation of this whole thing by replacing these HIs with their expectations.
There seems to be some problem here.
Okay? I'm sorry, can you start again?
So when we started, we were treating the H's as multinomial random variables. But here, we talk about the exponential family and the procedures down there.
Yeah.
That the H, there are L binary random
Yeah.
variables.
I'm sorry, I kind of skipped over that. So I mentioned that in the mixture of Gaussians. So yes, in this formulation, when you formulate a likelihood as a member of the exponential family, the HIs are binary.
Yeah, so we are not having each one to each n, but for each xi, we have H1 through HL.
Right, right. So if you remember when we defined the latent variables for the mixture of Gaussians, we said if you have L Gaussians and N data points, there will be N times L latent variables called H something. And it was Hij was 1 if data point xi came from Gaussian J. And 0 otherwise. So this is a common trick we use. Even though we could express the generative story in terms of latent variables that have multiple values, we choose to define for each latent event a whole set of latent variables. They're all binary. One of them is going to be 1 and the others are going to be 0. And that's the formulation that we need for this problem. Thank you. So let me just redo the mixture of Gaussians based on this formulation. Mixture of Gaussians known sigmas, known priors, known lambdas. The original likelihood function of x and h, I'd rather write it as h and x. That would usually be the case. I like to write the h first, simply because remember that I usually interpret it as the generative story, and in the generative story the latent event happens first and then the visible thing happens later. Conditioned on our mu's, which are our thetas, it's the product of the likelihood of each. That's what the problem is. I write it here as hi xi. So I'll tell you what, I'll use h for my latent event, and I'll use z for the binary variables that capture that latent event. So I'll do that here too, so we have an exact match. These are all z's. These are all z's. So I is an index that goes just from 1 to n, and it's the number of observed x's. So this is the likelihood of hi and xi given the mu's. Sorry. Now, I don't know the hi. So what I'm actually doing I'm writing it in terms of hi, but what I'm really after is the expected log likelihood. So expected log probability of hi xi given mu. And it's expected under hi, under a weighting of hi that depends on xi and on my mu, on my previous generation mu. So this is mu of iteration k. What is this expected log likelihood? And this is now summed over all the xi's, which could be either here or here. Since it's an expectation and a summation, it doesn't matter. If the likelihood itself is sum of lambda I 1 over 2 pi sigma e to the negative half x minus mu over sigma squared. This is j, this is I, this is j. Now I'm going to use the fact that it's part of the exponential distribution. So I could try to solve it using my very general formulation. It's going to get very ugly. But because I know it's a member of the exponential distribution, and he shows you here what the h is and what the g is, I can go straight to this shortcut. So I'm only interested, instead, only need to calculate the zij's. The zij's are defined here. And in fact, I don't need to calculate the zij, I need to calculate the expectation of each zij. What is the expectation of zij? It is the probability that the zij is 1, right? E of zij, since the zij's are all binary, E of zij is exactly the probability that zij equals 1, right? Now to be exact, this is expectation conditioned on the data I've seen. Sorry, I'm improvising a little bit. This is the expectation of zij conditioned on the data I've seen, which is xi in this case, and the current parameters. And I'm using theta here where I should use mu. I only need to calculate that, the conditional expectation of hzij based on the observed data and the tentative value of the parameters, the current value of the parameters. This is the probability that zij is 1 conditioned on what xi is and what the current value of the parameters are. Do you recognize this? This is the posterior. This is, assuming that this is true, how likely is this data point to have come from Gaussian J? That's the posterior you calculated when on Monday when we did the algorithm and we didn't call it EM. You calculated exactly this posterior. To remind you, it's lambda j e to the x minus mu j over the same thing but summed j prime, lambda j prime e to the negative x minus mu j prime squared over sigma squared. We did it with two Gaussians. We did it, here was A and here was A and B. So this is what we calculated those fractions. The fractions of a point, where to put the fractions. Now we can see it in general, it's the expectation of this binary random variable. So this is this step. You can call it the E step for the shortcut case. And now we need the M step for the shortcut case. And we said that the M step is to calculate, to maximize this expression here, to maximize this expression simply by taking where the HI's were supposed to be, or the ZI's were supposed to be, and replacing them with their fractions. And that's exactly what we did in the algorithm, if you remember. We calculated the mean of Gaussian A by taking all of the data points and including them fractionally. So that became the new mu j mu j of iteration k plus 1 was defined as the weighted average. You can think about it as sum of the zij's xi divided by sum of the zij's. You can think of it as a weighted average of the xi's weighted by how likely they are to have come from component j. So I don't know how much sense it made. Certainly EM is something that you need to go over again and again. The important take-home messages are, when is EM needed? We wrote it there. When does it come up? We wrote 3 cases there. What is its definition, the general case definition? We wrote up there. What does it guarantee? What does it not guarantee? What is the special case? The exponential family. And in the special case, what is the form of the algorithm? You have to define your z's. Okay? Always look at your latent variables, convert them into possibly more than one z for each latent variable. So if the latent variables take on more than 2 values, create a set of z's that capture that, where each z is only binary, 0 and 1. Then calculate the expectation of each z under the current set of parameters, and then take those expectations and plug them into the maximization equation as if these were the real values, as if we had fractions of the data points as opposed to whole data points. We will do it. We will follow this recipe again, the shortcut case, when we looked at the HMMs. And I think you will begin to get the flavor of it so that you can apply it in your own work. One other important thing to know about EM. EM is such a buzzword. Everybody does EM and wants to do EM. Just remember that all it's about is the maximum likelihood estimate. It's not going to give you the truth. It doesn't even give you the maximum likelihood. It gives you a local maximum. But it tries to give you something that's close to the maximum likelihood estimate. The maximum likelihood estimate is not always the best estimate. Right? Even if we didn't have latent variables, even if we didn't have the problem that we cannot solve analytically, you know from the first part of the course that the maximum likelihood solution, while interesting and having some good properties, is not necessarily the best one, especially in situations with very sparse data because of the high variance of the maximum likelihood solution. So you may want to think of ways of shrinking that solution or smoothing that solution. And there are variations on EM that give you smooth EM. Questions?
So about the exponential family, so after you have introduced the correct form of that family should be the sum is over j, zij, gj is not sum over zij, gi.
You're right, and I think the way he wrote it is wrong, so we'll need to correct that as well.
Yeah, and also on the left side is the p of xi and
P of xi, I'm sorry?
p of xi.
Yeah. Yep.
Yeah, I'm not sure about the c, but inside the exponential it should be the sum over
Right,
j.
so this is right. One second. Let me, and then this is sum over j, zij, thank you. Gj, yeah, and maybe he did write j and I misread it, I don't know.
Yeah,
And
so-
this is xi.
So
No?
although it looks complex, because these are binary, what this summation is doing
Is a product,
No, it's just choosing.
right,
Choosing the,
right.
Choosing
The right,
activity.
right. So because the zij's by construction can be either 0 or 1, and furthermore, for any value of I, there's exactly one value of j for which it is 1, and for all the other values of j, it's 0. This summation is basically a way of choosing one of the g's. And then once you choose one of the g's, it's the exp of that. So another way of writing it is that it's something that does not depend on j times e to the power of something, which is another something that depends only on the right j, on the correct Gaussian that was used to generate it. Question?
Do we update lambdas here?
Do I update lambdas here? In this version, I don't. So remember that the mixture of Gaussian problem has three sets of parameters. The priors, the lambdas, priors of the Gaussians, the means, the mu's, and the standard deviations. You can set it up in several different ways, depending on which of these you choose to be fixed and which of these you choose to maximize. You can solve all of them with EM, but the solution may be more or less efficient. So for example, if the only thing you're looking to maximize is the lambdas, that's a convex space. You can optimize it exactly. That's what you guys did in your homework. If the only thing you're trying to optimize is the mu's, it's a non-convex space, but at least it's a bounded space. If what you're trying to maximize includes the sigmas, it's not even a bounded likelihood space.
After changing this notation to Zij, what we should be calculating in steps 2 and 3 are all.
I'm sorry.
Just to clarify.
Yes, no, you're completely right. Easy IJ, easy IJ. Thank you. I mean, I've often struggled with should I use H or Z, and now I know I use both. I use H for the latent variables as we think about them, like which Gaussian was chosen, and Z for the binarization of that information, because Z is the way it's normally used in the literature. You'll see Z, you may not see H.
So it is open trick. So otherwise you put HI as a subscript of G.
Here? I guess so.
So J be replaced by H.
Yeah.
Yeah, you can put, yes,
G subscript H.
yes, yes. You could represent it as G that depends on H. But it's a trick, but it's not a trick that you can always use. You can only use it if the value of that G is, it can be written down as a linear sum of, in the log probability space, can be written up as a linear sum of independent functions that depend only on Z. So linear sum of the Z's.
But when the Z's are binary and there's only one and all the others 0, this should always be equal. Because that summation is just a choice.
Right. Well, I tend to think about it the other way around. Originally, you had a G that depends on H here. But if that G, it could be anything. But if that G that depends on H could be written down as a, since it's just a G that depends on H and it's e to that, it's still some other function that depends on H. But if that function can be written down as e to the power of something that's a linear combination.
Yeah, so it seems to me that the exponential here is not that important. The important thing is that the latent variable can be written as a set of binaries that has only ones. Only one, the other one.
A set of binaries
Yeah.
that are in the exponent, because you want to play that trick on the log likelihood. You want to push it in the log likelihood, right? So it has to be linear. The log likelihood has to be linear in those Z's. All right, I guess I'll see you Monday. We'll do HMMs.